We're going to start this video with the properties of the probability distribution for a random variable x. So first of all, you've seen something similar to this before, but let me just tell you that all of the probabilities for the random variable must be from 0 to 1. And if you sum up the probabilities of all of these values, they must equal to 1. So if you go back up here to the one I did in the previous video, each of these numbers ranges from 0 to 1, and then if you add up each of these probabilities, they add up to 1. So that's basically what's saying that has to be true for a probability distribution. Let's look at another experiment. Suppose that 3 coins are tossed and we're interested in how many of them land heads. Well, since I'm interested in how many heads occur, I'm going to let x represent the number of heads in a particular trial. And now let me list all the possible values that x can equal. X could equal 0 if I got no heads, 1 if I get 1 head, 2 if I get 2 heads, and 3 if I get 3 heads. So now let's look at the list. In this case, I can actually list all of the possibilities. I could get tail, 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 and then that way there would be 0 heads in that particular case. Or I could get tail, tail, head, which would give me 1 head, or I could get tail, head, tail, which is 1 head, or head, tail, tail, which is 1 head, tail, head, head, which is 2 heads, head, tail, head, which is 2 heads, head, head, tail, which is 2 heads, and then finally all heads would give me 3 heads. So now I could actually give the probability distribution for these values 0, 1, 2, and 3 by looking at this. So let's let this first row be the possible values of my random variables 0, 1, 2, or 3. And now let's let the second row be the probability of each of these. And you can see the probability of getting 0 heads. Notice there's 8 possible ways the coins could land, and there's only 1 way out of 8 to get no heads. So the probability of 0 heads would be 1. Now the probability of 1 head, notice there's 1, 2, 3 ways to get 1 head, so the probability of that would be 3 out of 8. And the probability of 2 heads is also 3 out of 8 because there's 3 ways that could happen. And then the probability of getting 3 heads would be 1 out of 8. And so that's the probability distribution. Now, we're going to introduce here something called the expected value of a random variable. Now, once you have this probability distribution like I had up here, once you have this probability distribution right here, then it's very easy to get the expected value of your random variable. Now, another word for expected value is mean or average. So really, this is sort of supposed to represent a long-term average if you were to perform the experiment over a large number of times. But the way to get the expected value is you simply take each value of the random variable and multiply it by its probability. And then when you're done, you add all of those up. So I would take x1 times the probability for that, then x2 times its probability, then x3 times its probability, and so forth until I get to the last one. And then I would add all of these up. Okay? So now let's return to my previous probability distribution. Notice here I have 0 times 1/8. So I'll put that there. Then 1 times 3/8 I'll put there. Then 2 times 3/8 I'll put there. And then 3 times 1/8 I'll put there. And then if I add these up, I'll get 0/8 plus 3/8 plus 6/8 plus 3/8. So if I add that up, I get 12/8, which is 1.5. Now what does this mean? Well, it means that if we toss these coins over and over and over, we would expect to average 1.5 heads per trial. And another way to think of this, if you did this a large number of times and your average was way off of 1.5, let's say your average was 2.5, then you would suspect something fishy about the coins. So, and then another way to look at it, suppose you did this experiment 100 times and tallied up the number of heads you saw. Let's say you counted 130 heads. Then you would simply say the average number of heads per trial is 1.3, 130 divided by 100. It's slightly lower than expected, but it really wouldn't raise an alarm. But again, if you got 2.5 for your average, then you might question if the coins are fair. Now let's go back to our test example. If you remember when we did that test earlier where we had 3 questions, we saw that you could get no questions right with a probability of 27 out of 64, 1 question correct with a probability of 27 out of 64, 2 questions correct with a probability 9 out of 64, and all 3 questions correct with a probability of 1 out of 64. So if we calculate the expected value of this random variable, we would take 0 times 27 out of 64, plus 1 times 27 out of 64, plus 2 times 9 out of 64, plus 3 times 1 out of 64. And then after you multiply each of these together and add them up, you actually get 48 out of 64, which reduces to 3/4 or 0.75. So basically, you would expect to average getting less than 1 question correct per trial. So now remember, a trial would be answering 3 questions. So if I had you do this, say, 100 times, you would expect to average, say, 0.75 correct answers per trial, or roughly 75 correct answers out of 100 trials. Okay, now again, they're not probabilities, so they can be greater than 1, they can be less than 0. So let's look at some more expected values. I won't spend time on this one because this one is really just like the 3-coin example, except it's a 2-coin example, and so you can just freeze the video and read this. But the probability of getting no heads is 1/4, probability of getting 1 head is 1/2, probability of getting 2 heads is 1/4, and then if you multiply each of these together and add them up, you'll get the expected number of heads to be 1. Let's take a look at this next one. It's kind of interesting. Suppose 3 cards are selected from a standard deck and we want to observe the number of face cards that occur. Well, let's let x be the random variable that represents the number of face cards that occur, and so x could be 0, 1, 2, or 3. Now, we know that if we let S be the set of all possible 3-card hands, then the number of elements in S would be 52 choose 3, which is 22,100. So, if we want to calculate the probabilities of each of these numbers, we have to use our counting techniques to get the numerator. We know the denominator is going to be 52C3 in each case, but how many ways can we get no face cards? Well, that would mean out of 12 face cards, choose none, and out of 40 non-face cards, choose 3. And then divide the result by 52 choose 3, and you get 0.4471. So notice down here in the table, for 0 face cards, I put 0.4471 as the probability. And then the probability that you get 1 face card, 12 choose 1 times 40 choose 2, divided by this denominator gives you 0.4235. And I put that down here below 1. And then here, the probability that x is 2 would be 12 face cards choose 2 and 40 non-face cards choose 1. Divide that by 52 choose 3 and you get 0.1195, and put that down here in this space. And then finally, the probability that x equals 3, that would be 12 choose 3 times 40 choose 0 over 52 choose 3, and that probability is 0.01. So now to calculate the expected value of that random variable, just multiply 0 times 0.4471, 1 times 0.4235, 2 times 0.1195, 3 times 0.01, and then add them all together. So you're expected to average 0.6925 face cards per trial. So I guess you could say 0.7 is a rough estimate. So you're expected to average about 0.7 face cards per trial. Okay, now here's another example. Suppose you have 2 4-sided die rolled and you wish to observe their sum. So let's let X represent the possible sum of the dice. Well, on a four-sided die, let's assume the numbers are 1 through 4. The lowest number you could get would be a 1 on each die, so that's 2. And the highest number you could get would be a 4 on each die, and that would be an 8. And there's 16 possible rolls because there's 4 rolls for each die, so 4 times 4 is 16. Now, let's think about the probability that you get a roll of 2, a sum of 2. Well, there would be only one way to get that, and that would be to roll a 1 on each die, and so that's 1 out of 16. Sum of 3, there's 2 ways to get that. You could roll a 1, 2, or a 2, 1, and so that's 2 out of 16. A roll of sum of 4, there's 3 ways to get that, a 1, 3, a 3, 1, or a 2, 2. Sum of 5, you could roll a 1, 4, a 4, 1, a 2, 3, or a 3, 2. So there's 4 ways out of 16 to get that. Sum of 6, you could roll a 2, 4, a 4, 2, and a 3, 3. So there's 3 ways. Sum of 7, 3, 4, and 4, 3. So there's only 2 ways out of 16. Then finally a sum of 8. There's only one way to get that, and that would be to roll a 4 on each die. So that would be 1 out of 16. So fill out the table and then multiply each of these by their probabilities and then add them up, and you actually get 5. So the expected value of the sum of the die is expected 5. Now that just means that the average, you're expected to average a sum of 5. It doesn't necessarily mean you'll always get a sum of 5. It just means that your average is a sum of 5. Okay, so these were just some basic problems where you calculate expected value. I'm going to do a little bit more advanced problems on the next video for calculating expected values, and I'll also do some problems that involve some gaming theory.